we discussed was frequency translation is the central concept of modulation techniques, right? So let's frequency translation. So you can recall very well, right? Frequency translation is we have a message signal which occupies some frequency range in the frequency spectrum, maybe 0 to FM hertz, right? And then we are translating that to another region in the frequency spectrum. This is the frequency spectrum, and this is the 0 hertz. And then say if the message signal is something like this, then we are translating this to some carrier frequency, very high frequency, so that the resultant signal will be something like this. This is what we discussed, and we discussed 4 advantages or 4 necessities of the frequency translation, right? If you can recall, so practicability of the antennas, and then multiplexing different signals, right? The first one, practicability of antennas, is the antenna size dimensions are proportional to the wavelength of the signal to be radiated from the antenna, and hence it's better to have it's better to have a high frequency signal to be radiated from the antenna. So that was the first one, and then the second one was let me write antennas. Second one was multiplexing, because say if you take all of the message signals may occupy the same band. Say if you take the speech signal 0.3 kilohertz to 3.44 kilohertz, or audio signal 50 hertz to 10 kilohertz, and it's difficult to differentiate them if all of them transmit in the same band. So multiplexing is we translate different user signals to different regions in the spectrum and then transmit them. Right? So this is called frequency multiplexing, frequency division multiplexing. That's what we discussed. And then third one was narrow banding. We want to make the effective signal look narrowband. So if you consider the audio range from 50 hertz to 10 kilohertz, the dynamic range is quite high, f max by f minimum. And even assuming you can design antennas for low frequencies, the antenna which you designed for 10 kilohertz is not good to transmit 50 hertz signal, or the antenna which you designed for 50 hertz signal is not good to transmit 10 kilohertz signal. And also it's always better to have a low dynamic range for the circuits or whatever. So when we translate this 50 hertz to 10 kilohertz to say 1 gigahertz or 1 megahertz, then effectively f max by f min is becoming very low. The ratio of f max by f min is coming out to be low. So what is a narrowband signal? If you can recall the definition, with respect to its central frequency, if the bandwidth is very low, if the bandwidth of a signal with respect to its central frequency is very low, very small, then we call that as a narrowband signal. Right? So then the fourth one, I said ease of processing. Right? But this I said we will discuss when we discuss the AM receiver, amplitude modulation receiver. So yeah, we'll do that later. And then we have quickly seen this, how do we do the frequency translation, right? We did, so this is all recap of last class. We'll finish it off in 2 minutes, then we'll go to the new content that we'll discuss in this class. So frequency translation. Through multiplication. Multiplication of what? Of 2 signals. What 2 signals? The say Vm of t is a message signal, right? And we want to multiply that with Vc of t, which is the carrier signal. And then say if we first considered Vm of t is simple cosine signal, sinusoidal signal, cos 2 pi fm of t, and then we saw that the spectrum gets shifted, and then we discussed this m of t. We have discussed m of t as a message signal of non-zero bandwidth. Why do we call here non-zero bandwidth? Because the bandwidth of this signal is 0, right? It doesn't occupy any band. It's just one sinusoid, one impulse in the frequency domain. So but our message signals are of finite bandwidth. So we considered a message signal of finite bandwidth, and we showed that m of t multiplied by Vc of t, which is equal to m of t AC cos 2 pi fct. So that resulted in, say, through Fourier transforms we proved this. Say m of t, its Fourier transform is m of f. Then we showed that m of t Vc of t Fourier transform is of m of f plus fc, right, plus m of f minus fc. So through multiplication, we showed mathematically that we can translate a signal into another region in the spectrum. Like we can translate. So if you recall the diagram, so what I said was, say this is some m of f, right, and then this is fm. The bandwidth is fm. And then we, by multiplying that, we translated that to, say, this is fc, this is fc plus fm, this is fc minus fm. Similarly here minus fc, and then we have this. And then I also asked you to check, why do we consider frequency spectrum of the signal to be symmetric with respect to origin, right? Because unless the frequency spectrum is symmetric with respect to origin, unless it's Fourier, so sorry, it's the magnitude of m of f always. Unless the magnitude is symmetric, like and phase is linear, it is no more a real signal. So this is all we did in the last class, right? So now let's come back to the current class, like, right? Yep. And yeah. So today's class we will start with a couple of definitions or new terms which we would like to introduce. So a couple of like what are this is, say we have seen that. So one of these things is yeah, baseband spectrum or baseband, okay, baseband signal or baseband frequency range. Right. So this message signal m of t is called baseband signal. So this is m of t, and what is baseband frequency range? Say I have shown you this diagram, right? Say the baseband signal may be having some spectrum, something like this, or in any spectrum which is symmetric with respect to the origin. So this is m of f, and this is the maximum frequency. Let's say this is f of fm. Yeah, maybe we should use small m. Yeah, fm, and this is minus fm, right? So this frequency range 0 to fm is called baseband bandwidth, or the frequency range of the baseband signal. So 0 hertz to fm hertz, this is called the baseband frequency range. Simply baseband we call it, and as we have seen here, this is the m of t is called baseband signal now. So the, yeah, and this operation, see, we are multiplying with vc of t, right? vc of t we are multiplying, and that is called cos 2 pi f ct. So this cos 2 pi f ct, or this vc of t is called carrier signal. This we have used in the last class, and we always said this is the carrier signal. So there is nothing new in this. So vc of t is a carrier signal, and this is also called, this sometimes it's also called, so let me give you that so that you won't get confused if somebody mentions this, also called local oscillator signal. Yeah, just a minute. So local oscillator signal, and it's also called heterodyning signal. Because maybe if you read some other textbook, maybe you will find a different term for this, right? So you just note it down that it's also called local oscillator signal or heterodyning signal. You will come to know why it is called so. But we'll stick to this term carrier signal. This more meaningful to use this word carrier signal, right? And we have to define what is this multiplication. See, what we said was, for frequency translation, we were doing multiplication of m of t with AC cos 2 pi f ct, right? So this multiplication is called mixing or heterodyning. That action of multiplying multiplying m of t with vc of t is called heterodyning or mixing. Okay, these are just few terms that you have to be comfortable with. Yeah, whenever you read something, or whenever there is a question, or whenever. So yeah. So now it's time for us to define what is this. So now let's again closely examine this m of t into vc of t, which is equal to AC cos 2 pi f ct into m of t. So we are writing this equation again and again, but yeah, so this may be. So now let's simply look at this. So now, previously, if you consider vc of t, is only this, right? It's a sinusoidal signal with frequency fc, and it has got a peak amplitude of AC, right? Now after multiplying what we are getting is its amplitude is getting changed to AC m of t cos 2 pi f ct. Right? So this is now the effective amplitude of the of a sinusoidal signal at frequency fc. And remember we said that fc is much greater than fm. What is fm? The bandwidth of the message signal, right? So that meaning by this, through this multiplication, what we are doing actually, we are varying the amplitude of a high frequency signal. So this is a high frequency signal or carrier signal that we were talking. So it's AC cos 2 pi f ct, and its magnitude is now getting varied with respect to the message signal m of t, or in accordance with the m of t, right? So we are varying the magnitude of a high frequency signal cos 2 pi f ct in accordance with the message signal m of t, and that's what precisely we defined as a modulation, right? Modulation, how did we define? Modulation was varying one of the parameters of a high frequency signal in accordance with the message signal. That's what we said in the very first class. And then we said, what are the parameters of the high frequency signal? Frequency, amplitude, phase, right? So here we are varying the amplitude of the high frequency signal with respect to the message signal. So as we are varying the amplitude, it is called amplitude, right? So hope you got it. Like we just defined modulation as the process in which one of the parameters of a high frequency signal is varied. The parameters we defined was either frequency or amplitude or phase. And then here, after this multiplication, what we observed was the amplitude of a high frequency signal cos 2 pi f ct is getting varied in accordance with the message signal m of t. So this process, so through this process, we implemented an amplitude modulation, right? So what we did by multiplying m of t with a high frequency carrier signal AC cos 2 pi f ct. See, this AC, you need not give much importance to this amplitude. It can be taken as 1, right? Like we will see it's the role played by AC, but here it's simply constant, right? So don't get confused much by this AC. It's just a constant peak amplitude. So by multiplying m of t with a high frequency carrier signal AC cos 2 pi f ct, okay, we achieved amplitude modulation. Why did I say amplitude modulation? Because the amplitude of the this high frequency signal is getting varied in accordance with m of t. Now let's be more precise. Like let's specify it more carefully. What do I mean by that is, so yeah. So what kind of a what kind of an amplitude modulation is this? So this is called, okay, so let's see that. Okay, let me again draw this diagram, or let's go back to the previous slide rather than drawing it again and again. Sorry for that. Yeah. So let's see here. So after multiplication, what do we have? So we have this as the original signal, right? This is our baseband signal or the message signal occupying frequency FM and minus FM. So its bandwidth is FM hertz, and then we multiplied that with AC cos 2 pi FCT, and then its amplitude got reduced, but in frequency it got translated to FC minus FM to FC plus FM, right? So uh, after multiplication, okay, we need to introduce two more terms here. So this is called upper sideband, and this is called lower sideband. So this is USB, this is LSB, right? The frequency range, the signal occupying the frequency range FC to FC plus FM is called upper sideband signal. So I'll write this in a minute. This is called upper sideband, right? And this, the frequency range in the translated signal occupying FC to FC minus FM or FC minus FM to FC is called lower sideband signal. So that means we have both upper sideband and lower sideband signals. And remember, just realize that there is no carrier signal here in the translated thing. So with that, let me write down that. Yeah. So sorry, I should have defined this. Upper sideband is, we call it USB. So signal occupying frequency range from FC, sorry, from FC to FC plus FM hertz, from hertz after frequency translation. So consider the signal after frequency translation. And in that, the signal occupying this range is called upper sideband. And similarly, the lower sideband is FC minus FM hertz to FC hertz. So this signal is called lower sideband signal. So after multiplying, what are we getting? We are getting double sidebands, both the sidebands, like upper sideband as well as the lower sideband. And obviously we are in the resultant frequency translated signal, there is no carrier signal. What do I mean by carrier signal? So in the frequency spectrum, if we see an impulse at FC, we call there is a carrier signal present in the spectrum. But do you see in that diagram? No, right? So please bear with me. I'm going back to that figure again. Though it takes 1 minute, like it's better to go to that figure rather than drawing it all over again. Yeah. So in this, you see there is no impulse at FC. If there is an impulse at FC, that means there is a carrier present. Now we have simply the baseband signal, right? There is a baseband signal and translated in frequency. So this we are calling it as upper sideband, this we are calling it as lower sideband. So what do we have is double sideband suppressed carrier signal after multiplication. So this is called double sideband suppressed carrier amplitude modulated signal. So yep. So we have DSB SC. So what is this? Double sideband is called double sideband suppressed carrier signal. So simply by taking the message signal m of t and multiplying that with cos 2 pi f ct, okay, to be precise AC cos 2 pi f ct, we obtained double sideband suppressed carrier signal. Yep. So just as you have done the Fourier transforms well in your previous semester or last year, I don't know which year you did it, but see if there is a signal, if the signal is symmetric both with respect, say, yeah. So just take this. So in this case, the Fourier transform of the signal, right? The Fourier transform of the signal is symmetric. The magnitude of the Fourier transform of the signal is symmetric with respect to the origin. Then, if you have only this upper side band, or what you call, if you have only the signal from 0 to FM, that's enough for you to determine the signal, right? Okay. Anyway, so let me not confuse you. We'll discuss more in detail later. So what I'm trying to say is only one of the sidebands is enough for us to get back the original signal. So anyway, so this is, yeah, forget about that single sideband and double sideband, but this is double sideband suppressed carrier signal, right? Now, how to achieve this? Listen, see, just through maths, we showed that if you multiply this message signal with the carrier signal, you get amplitude modulated signal, and the amplitude modulated signal is having both the sidebands, upper sideband and lower sideband, and it has got no carrier in the output signal. That's why we call it double sideband suppressed carrier signal, right? But how do you have it in circuits? Like say if you want to implement, right? Say our engineering task is to not only the math, but math is the language of the engineers. It helps us to analyze and build systems, but ultimately you have to realize that system, right? So let's think about one modulator. So see, as there can be n number of, there can be multiple ways of achieving this modulation through circuits. So what I'm trying to say is, let's examine just one modulator, one amplitude modulator, which produces double sideband suppressed carrier signal, right? So we are considering one modulator. So as a word of caution, there can be, not there can be, there are multiple ways of generating double sideband suppressed carrier signals. Or equivalently, there are multiple ways of doing the amplitude modulation, which gives us double sideband suppressed carrier signals, right? So yeah, let me look at my notes. So let's consider this particular modulation, this particular modulator. Say we have m of t, and we have an adder here, and to that we are supplying cos 2 pi f ct, right? And then, right, so it's an adder. This symbol just represents there is a circuit here which adds m of t with the cos 2 pi f ct. So cos 2 pi f ct is the carrier signal with peak amplitude of 1, right? And then let's call its output signal as v1 of t, and let's give that to a device which has got, which is a second order, so this is order, second order nonlinear device. So is this clear? So this is, we are just representing a device with a black box. That device has got that device is a second order nonlinear device. Let's call its output as W1 of t. Right? So what we are trying to do now, we are trying to build a circuit, or yeah, it's not a circuit exactly, in the sense we are not showing what value of resistors, capacitors, or diodes or transistors we will be putting in. We are trying to show a block diagram level view of a modulator, right? So if we have a second order nonlinear device, and then a circuit which results in DSB-SC signal. Okay, so the second order nonlinear device, so yeah, maybe let me, so let me write this here. So I'm writing this again here because we have to expand this diagram later. You will understand what do I mean by expanding this diagram, right? So this is second order nonlinear device. I'll tell you in a minute what this is. Say this is V1 of t and its output is W1 of t. Right? So just remember this diagram. We'll come back to this page because we need to fill in some more blocks here. We'll keep building that, right? So now hope you have copied this to your notes, and then now what is the second order nonlinear device? W1 of t is some A into V1 of t plus B into V1 square of t. So this is the input output characteristics, just like your VI characteristics, input output relation of the second order nonlinear device. So assume we have such a device. See, in your other courses, you should think, when you are doing other courses like your devices and circuits, say class C amplifiers and all, like, so I'm just like, I'm not an expert on circuits and systems, like the electronics part of it, but it's, you should think, how do you, which circuit or which device will have such a characteristic, right? So you should think, you should discuss when with your friends and with your teachers, how do you, what device could have this kind of characteristics. So if you give a V1 of t signal as input, its output should be proportional to some constant A into V1 of t into some plus some constant B into V1 square of t, right? So see, this is the way you learn. Like, you should discuss with your friends and faculty members, like, or think about yourself, or go through some of the books, what kind of device or circuit will have such a characteristic. So in this course, our focus is not exactly to go into those devices and such thing, but we assume that such a device exists, and assuming that, we will build our amplitude modulator, right? So just not to have more clarity, I will write this: A and B are some constants. They depend on the device, right? Okay. Now with this, let's examine. So what is our V1 of t? V1 of t is the output of the adder. what are the inputs to the adder? M of t plus cos 2 pi f ct, right? Now W1 of t is A into M of t plus cos 2 pi f ct plus B into M square of t plus cos square 2 pi f ct plus 2m of t cos 2 pi f ct. Is that right? Because to the just look at this. So my v1 of t is m of t plus cos 2 pi f ct. So that's why my w1 of t is a into v1 of t plus b into v1 square of t. So this is a into v1 of t plus b into v1 square of t, right? Okay. Now, do you think this w1 of t is the desired signal for us? Yeah, I would love to have interactive classroom, but yeah, so yeah, anyway, so we are through a distant learning mode. So you can see that this W1 of t, see what do we want? What is a double sideband suppressed carrier signal? We want simply m of t into cos 2 pi f ct, right? What we want at the output is m of t into cos 2 pi f ct, and there can be some constants like 2, 3 or whatever, a, b, whatever. So there can be some constant k and m of t into cos 2 pi f ct. That's what we want. But what do we have here? We have so many other terms like cos square 2 pi f ct, m square of t, m of t, cos 2 pi f ct, and so on. Right? So let me write. We want some k, where k is some constant, into m of t into cos 2 pi f ct. Where k is some constant. Right? So let's call this, yeah. But here we have some 2 into b into m of t cos 2 pi f ct, but we have a whole lot of other terms. Okay, now how do we cancel these terms? So let's, right? So you understood the problem. We have some unnecessary terms. Now let's consider uh, yep. So let's consider, yeah, sorry. Consider now another circuit, right? So let me, so I came back to the original diagram. As I said, we have to fill in some details, right? So now we have minus m of t. And we have same cos 2 pi f ct here, right? And then let's say its output is v2 of t. And then we have the same second order nonlinear device here. Let's call this out, right? So here is the carrier signal source. We are giving the same thing to another adder, and here instead of m of t we have minus m of t, and then we are calling that. So what is v2 of t now? Minus m of t plus cos 2 pi f ct. right? V2 of t is equal to minus m of t plus cos 2 pi f ct, and that we are giving to the second order nonlinear device, and we are getting an output wt of t, and then this is the same, this has got the same characteristics as the above second order nonlinear device. So wt of t is 2 of t is a into v2 of t plus b into v2 square of t. So now consider the second branch or the lower branch, right? Consider the lower branch. So v2 of t is minus m of t plus cos, and what is wt of t? W2 of t, sorry. So this is a into minus m of t plus cos 2 pi fct. Yeah, just a minute. Yeah, plus b into m square of t plus cos square 2 pi fct minus 2 m of t cos 2 pi fct, right? Yep. Now we have w1 of t. Okay, so this clear, right? So wt of t is this, and let's consider the previous space. So in the previous space we have w1 of t, which is this equation. Now we have w2 of t, which is this equation, and let's do w1 of t. Yeah, let's do w1 of t minus w2 of t. So what that will be? That will be 2a m of t, right? And this cos terms, this term will get cancelled, these terms will get cancelled, plus 4 m of t cos 2 pi fct. Right, you got it? You can take a minute to see how it came. It's just nothing but some arithmetic addition. We have w1 of t in the previous space, and then we have wt of t now, and then we subtracted w1 of t, w2 of t from w1 of t, and then we got this, right? Okay. Yeah. See, this is our desired signal, right? What do we want? Do you remember? We wanted something like k multiplied by m of t multiplied by cos 2 pi fct, right? So but what do we have here? 2a m of t into 2 into a into m of t plus some 4 into m of, oh, okay, sorry, there is something called b here. Yep. So because this b will be here, right? Yeah. So this is unwanted signal, right? Now how do we get rid of this signal? Now we have achieved, we are close to our desired result, right? See, earlier we have all these terms. In w1 of t we have m square of t cos square cos 2 pi fct, all these things. Now we got rid of many of those terms. We just have one term here. So And you must be knowing by this time, because from your signals and systems course and all, you must have come across filters, right? So what are filters? Low pass filter, high pass filter, band pass filter, band gap filter, right? At least you should have known the definition. I'm sure about that. So what is a low pass filter? It passes low frequency around the 0 hertz. High pass filter passes the high frequencies and it suppresses all other frequencies. And then what is this other thing? Band pass filter. So what is a band pass filter? So let's examine what is a band pass filter. Passes only a certain set of frequencies in a particular band, right? So if we have, okay, so okay, maybe I should ask you rather than giving you the solution. So just examine the signal W1 of t minus WTU. So let me do one thing. So the spectrum or the Fourier transform of W1 of t minus W of 2 of t contains, so this is 2a into m of t, right? Say, sorry. Say this is a, so this is 2a into m of f, and then so this corresponds to 2a into m of t, and then we have fc. Oh, sorry, my diagram is not that good. Yep. So it should be something like this. And so minus fc, right? So this is fc plus fm, this is fc minus fm, and this is minus fc plus fm, and this is minus fc minus fm. By this time you can draw this very well. So this is fm, so this frequency is minus fm. So this is the spectrum of W1 of t minus W2 of t. But what do we want? We don't want this central signal. We don't want this signal, right? And we want only these two signals. See, my diagram is not very accurate. The distance of fc from 0 to fc should be same as 0 to minus fc. So you please draw proper diagrams. So I may be like, yeah, little, I'm not that good in drawing diagrams. So anyway, so now let's think of a, how do we extract these two things. See, what we want is double sideband suppressed carrier. We don't want m of t. So use band pass filter with its spectral characteristics as follows. So can you draw it for yourself? Like I want a band pass filter. So I have this signal as the input signal to a band pass filter, and I want the band pass filter to pass only these frequencies, but I want this to block this. So obviously the band pass filter characteristics would be, it should have a flat frequencies. Yeah, sorry, again, yeah. So we want a band pass filter having this kind of characteristics. So band pass filter should pass the frequencies only. Say this is minus FC, this is FC, and this is 2 FM. So this is 2 FM. So I should have a band pass filter having characteristics like this. It should pass the band of frequencies from FC from FC minus FM to FC plus FM, right? And it should not pass any of the lower frequencies. So that's all. We got it. Like you apply the W1 of t minus W2 of t to a band pass filter having such a characteristics, right? And then you get your double sideband suppressed carrier signal. Understood? Right? So now let's complete this diagram with that knowledge. So whatever we have W1 of t, W2 of t, and then mathematically we have seen that if I perform W1 of t minus W2 of t and then give that resultant signal to a band pass filter, my output will be some k into m of t into cos 2 pi fct, right? So let's complete this diagram. See, you can complete with just with a little thought. So now we have this, right? So let's give it to a adder again. Here I will multiply with minus 1 and then give this to adder. So this resultant will be W1 of t minus W2 of t, right? So this output I am giving it to a BPF, band pass filter, and its output will be, what is this output? 4B m of t into cos 2 pi fct. So this, what are the characteristics of this band pass filter? It should have a pass band, this FC plus FM, this is 0, this minus FC, so this is FC minus FM, right? Got it? Okay, so this is the block diagram of a DSB-SC modulator, right? So see, so some of you may as well write, you may not write multiplying by minus 1 here. You can simply put minus sign here, right? So in some of your block diagrams in other courses you will do that, but it's up to you, like whatever you want to do. So there is one adder here, second order nonlinear devices, and then we got W1 of t, W2 of t, and then the resultant, and then it is sent to a BPF, band pass filter, and the output is this. So this is our desired output. Okay. Okay. Sorry. Let me keep it for one more minute. Yep. So yeah, so that is one modulator, one double sideband suppressed carrier modulator built using nonlinear devices. Fine. So yeah, if you have any questions, so I gave my WhatsApp number to the technical staff at JNTU Kakinada. So they must be passing it on to you. So we can have some, like, if you have any questions, you can email me. Um, yeah, I can share my email. Like I have put it in the first class, and also you can send it over WhatsApp. But WhatsApp I don't prefer much because you cannot write long sentences and write math symbols on WhatsApp. Yeah. So anyway, with that, I just want to take 5 minute break, and then we'll come back. We can discuss. So okay, let me. Uh, just assume a switching modulator. So this is, it shows a modulator something like this. This is the message source M of t, right? And then the output of this switch goes to something called BPF. So this is the output signal. And this switch, right, this switch so sorry, switch operates at FCH, right? So FC is okay. So before going to switch, so let me write all the specifications of the problem, then we will solve it. Like say M of t has maximum frequency component, at FM hertz, right? So M of t has got a bandwidth of FM. Basically, it is a baseband signal having some spectrum from 0 to FM hertz, right? And then this switch is operating at FC hertz, where FC is much higher than FM. So as FC is essentially the carrier frequency. And then also let me tell you what do we mean by the switch operates at FCH. That means the switch closes and opens at the rate of FC. And then the on off periods of the switch are equal. So let me write that down. So the on off duration of the switch are equal, and it is on and off at a frequency of FCH. Yeah. So what do we mean by that? Like, is that, say, how do you realize such a switch? See what the problem is saying. What the problem is. So consider this circuit. So assume that there is a switch which operates at frequency FC. So and it is on and off for an equal amount of time. So essentially, what we are trying to say is we want the switch on off pattern should be something like this. The switch is on and the switch is off. On. So this is switch is off and this is switch is on, right? This is again on, this is off, like this. So this is on, off, off, and so on. And this frequency is sorry. And this is over FC. So this is time axis, right? And this is 1 over FC. So what is this? 1 over 4 FC. And this is minus 1 over 4 FC. So the switch is getting on and off at the frequency of FC, and the switch is on for 1 by 2 FC and off for 1 by 2 FC. So on period 1 by 2 FC, off period, sorry, this, yep. So off period 1 by 2 FC, and it's right. So essentially the problem is saying that we have such a switch there, right? So this switch is such a switch, and then there is a message signal m of t applied to that. So m of t will pause for some time, and then or effectively this is equivalent to multiplying m of t with some signal waveform. So this switch we characterize it switch, right? So now the question is, before going to show that whether this actually does the amplitude modulation, the double sideband suppressed carrier or not, let us see how do we realize such a switch. So and one part of the question in that example is how do you realize such a switch? So I'm sure if it is like yeah, generally what we do, what I do in my classes is such a question can be given for 5 minutes of time, and then like how do we realize such a switch, and then students will come up with some solutions, some new solutions, or some people will solve it, some don't solve it, but then we'll discuss that in detail. But yeah, maybe we don't have that luxury of instant feedback here. But so one solution given in the book is this. Say you have with diode, for my poor drawing skills, but if you have, yeah, I know this is a very bad diagram, but it will serve our purpose. That's more important. So this is here you apply cos 2 pi fct to these two terminals, and from here you take the output, right? So what essentially this does? So the cos signal is something like this. Right? So assume that is a cos signal. I know that is not exactly a cos signal, but so its frequency is 1 by, yeah, so this is 1 by fc, right? And then what do we have it here? So yeah, so because of this circuit, this is the on period. The signal flows during this time. It won't flow this time. The signal flow during this time. It won't flow this time, and so on. So this square wave shows when the signal flows and when it doesn't flow, right? So this is one kind of a switch we can make with diodes, simple diodes. So we achieved this, right? Like see, compare this diagram, with this diagram. So we wanted a switch which exactly does this. This is 1 by fc, this 1 by 4 fc, and you see this is also same. This 1 by fc. So this 1 by 4 fc, this minus 1 by 4 fc, and so on. Or another way of realizing this is something like this. Okay, let me not discuss that. If you okay, let me put this like this. Think how to realize such a switch operated by cos 2 pi f ct using a digital switch. So we can discuss this later, but our time is getting, we are running out short of time. So what do I mean is, yeah, let me give you simple hint that you use comparator. Yeah, as I said, I'm not a circuits guy, so I'm not an expert in this, but I thought of constructing another circuit, something like this, which you can try on your own in your lab in your leisure time, using comparator and then a digital switch. So what is a digital switch? Digital switch, like there are ICs having four digital switches. So the digital switch will have an input and it will have an output, and this is the control signal. So if the control signal is high, the switch closes. If the control signal is low, the switch opens. Say in this case, so if the control signal is plus 5 volts, the switch closes. If the control signal is 0 volts, the switch opens. And then using a comparator and a sinusoidal signal generator and a digital switch, you can realize an alternative way of generating this switch. So this is the switch given in the textbook. That's fine. But you can also do this using digital components. That's what I'm trying to say. So right, this could be a simple fun exercise for you guys. Maybe you can just get into a lab when you have some free time. Right. Okay. So our task is not how to exactly design the switch. Our task is to show that this diagram does double sideband suppressed carrier. Right. So now how to show that the switching modulator generates DSBSC. Okay. Now we know that the switch is on and off, right? So we have the signal M of t, and we have the switching switching signal means the switch becomes on and off at this period. So we have this switch, we have this signal. So this is 1 by Fc, this is 1 by 4 Fc. So let's call this as a switching signal S of t. This is time, right? So just again go to maths. Like this especially communications is nothing but applied maths. Okay, so that you will realize that you would have felt something when you did signals and systems course, which is the base course for any communications or signal processing engineers. And then analog communication, you will see the mathematical description and then translating that into the circuits, and then digital communications. So it's all nothing but we use math to understand concepts and then go to electronic circuits to realize those concepts. Okay, so now we have this M of t and the switch is getting closed with and the switch on off pattern, the switch on off pattern is given by this pulse, this waveform. Say here also let me call it as S of t. So that meaning essentially what this circuit is doing is it is multiplying M of t with S of t and then it's giving that output to the BPF, right? So you can in an abstract manner, in mathematically what you can think of it as M of t is getting multiplied by the switching pattern, the switching signal which is S of t we derived here, and then that output is being fed to the BPF, right? So let's see, M of t is getting multiplied and the output is given to the band pass filter. So that's what we can conclude, right? So now what is M of t into S of t? So we have to think of what is M of t multiplied by S of t, right? That's the question we solve now. So if we solve this multiplication and then give that output to BPF and then examine the output of the BPF, then we should know whether it is a double sideband suppressed carrier signal or not, right? So how do you describe this S of t? See, S of t I have drawn only the diagram, right? We have only the pulse waveform. It's the pulse is on off with some amplitude 1. Its duty cycle is 50%. It's on for 50% of the time, off for 50% of the time. That's it. But we haven't given any mathematical description. But in order to multiply M of t with S of t, we need to have a mathematical description of S of t, right? So now let's go back to Fourier series. Yeah. So what is the Fourier series? So this is why I asked you to refresh your basics of Fourier series, right? So in I'm sure in your signals and systems course, you should have done. I'm sure about this because it's one of the standard examples. See, you should have solved a problem which is something like this. Say consider. Say this is tau by 2. This is minus tau by 2. This is T naught. Again, this is tau, right? This is tau. This duration is tau, and similarly, this is 2t naught. Again, this duration is tau. Minus 2t naught, and so on and so forth. So this is tau. I'm sure you must have solved. If this is the signal, what is the Fourier transform of such a signal? Fourier series expansion of such a signal is a tau. So let me see my notes. I did it this morning. A tau by t naught plus 2a tau by t naught into sigma n is equal to 1 to infinity sin n pi tau by t naught into cos of, sorry, I went very far, cos 2 pi and t by t naught. Right, the Fourier series is given by this. Fourier series of this signal is given by this. So just now, our signal, the switching signal is exactly similar to this, right? So okay. So let me tell you that, do it as a homework, right? So take such a signal. Maybe you have readily in your notes, in your signals and systems notebook, but go and derive it, because if you are given a new waveform and asked you to show whether it does amplitude modulation or not, then you should be able to analyze things, right? So you should know the problem solving skills. So you go and check this out as a homework problem. So the Fourier series expression of such a waveform is this. Now why are we considering such a waveform? Because our switching waveform is exactly similar to this, right? Is very similar to this. So let us see that, like, so this is our switching waveform. Where is that? Yeah, right. So this is our tau is what? See, it is on for 1 by 2 fc, off for 1 by 2 fc. So that meaning our switching waveform s of t is similar to the above waveform. When I said above waveform, this is the waveform with tau is equal to 1 by 2 fc. Yeah, sorry, I haven't mentioned what is a. So the amplitude is a here, right? So this a is the amplitude of these pulses, tau is this duration, t naught is this duration, right? Okay. So our switching, if you compare this waveform with our switching waveform, so we can say that tau is 1 by 2 fc, t naught is 1 by fc, and a equal to 1. So in this waveform, what I'm trying to say is, if you put tau is equal to 1 by 2 fc, t naught is equal to 1 by fc, and a equal to 1, then you get our switching waveform. So this is a switching waveform, and let me put this amplitude as 1 here. right? So I hope I'm not confusing you, right? So this is the thing. Now yeah, we have a, we can express S of t as a tau by t naught, right? A is 1, a tau by t naught, so which is equal to a equal to 1, tau is 1 by 2 fc, t naught is 1 by fc. So this is what happens, this is equal to 1 by 2 plus, what do we have, 2a tau by t naught, so this is plus 2 by 2 into n equal to 1 to infinity sin n pi tau by t naught divided by n pi tau by t naught. So that meaning we have n equal to 1 to infinity sine of n pi by 2 divided by n pi by 2 into, what do we have here, 2 pi n t by t naught. So this is equivalent to 2 pi n fct, right? So this is equivalent to half plus this 2 gets cancelled, and this is 2 by pi into n equal to 1 to infinity divided by n cos 2n pi fct. Okay, right. So now this can be written as half plus 2 by pi. Yeah, I know that the time is over, 10:40, but let me take just 5 more minutes, and then so that we can come to a end of this topic, right? Just bear with me for 5 more minutes. Okay. So and then yeah, see here you can do simple calculations. For all even values of n, this becomes 0. Do you agree? When n is even values 2, 4, 6 and everything, this will be, this numerator will be 0. So this entire term will become 0, right? But for all odd values of n, this becomes plus minus 1. So what I'm trying to say is, so this will be cos 2 pi fct minus 1 by 3 cos 6 pi fct plus 1 by 5 cos 10 pi fct minus plus minus plus minus plus. That's it, right? So my only request is just check from here to here. Yeah, it's obvious for you guys who, this just like very obvious. For all even values of n, this becomes 0. For all odd values of n, this becomes this varies between plus and plus minus 1. That sign value, right? So yeah, we have this. Now we have S of t expression, and this S of t is getting multiplied. This S of t is getting multiplied with m of t. So now just imagine that m of t multiplied by S of t will be m of t by 2. So this whole expression will get multiplied by m of t, right? Plus 2 into m of t by pi into all this stuff again, cos 2 pi fct minus 1 by 3 cos 6 pi fct plus, and so on, so forth. Okay. Now this is the output of the switching circuit. This is going to the band pass filter. So do we know what is band pass filter doing? No, I didn't tell you, right? That's a mistake. Like I should have told you what is the characteristics of the band pass filter. So hope you have noted down this one. Like this is nothing very complicated. Just a straightforward expansion of the Fourier series, and then just multiplying m of t with s of t. Yeah. So I forgot to tell you that band pass filter passes signals in the range fc minus fm, yeah, plus or minus fc plus or minus fm. That meaning, so band pass filter has got this characteristic. So this fc minus fm, this fc plus fm, minus fc plus fm, minus fc minus fm is the BPF characteristic, right? So if now m of t s of t is input to BPF, so BPF output will be m of t by 2 plus 2 by pi. Okay, let me go back once. So this signal will not be filtered by the BPF. So all these signals will be filtered out. So this is 2 by pi m of t cos 2 pi fct. So this is 2 by pi m of t cos 2 pi fct. Yeah, sorry. The output will be okay. So see, this m of t cos 2 pi fct has got frequency components from fc minus fm to fc plus fm. So this signal alone will be passed by the BPF, and even this signal won't be passed by BPF, and on all the next signals won't be passed by BPF. So the BPF output is 2 by pi into m of t cos 2 pi fct. So what it is doing?